This video is an introduction to the unit circle. Now, as an overview, in any topic, we always want to make sure to read through the textbook and take good notes, writing out all definitions, read all the examples, and note any points of confusion or questions, write out or copy by hand any diagrams or charts. The textbook is a more thorough take on the details in a topic. This video is meant to provide some important highlights. Now, I want to begin with what I'm going to call special fractions of the unit circle. And these special fractions, though you may not consider or see them called that in the textbook, these special fractions are going to be the foundation for us using and understanding the unit circle. To get a basic idea of where these fractions come from, we're going to use the image of an analog or circular clock. Now, we're not going to use it to tell time, so don't worry if that's not your favorite form of a clock. But this will help us get a good visual image that will help us understand just some of the fractional ways we're going to be using a unit circle. So to review, understand that a basic analog clock has numbers around the outside. It's a circular shape. At the very top of it, you'd have the number 12. And then if you move down the right side from the top of the circle, we call that clockwise direction. That's the way the hands on a clock typically move. And you'd find the numbers 1 and then 2. As you keep rotating around, you'd see a number 3 on the right side of the circle. If you kept going downward, you'd see the number 4, 5, and then a 6 at the bottom. And again, this direction is called clockwise. It's the way the hands move, but we're not even looking at clock hands because we don't care about that direction at this moment. If you kept going around the clock, you'd start going up the left side now. So you'd see a 7, an 8. You'd see a 9 on the left side of the clock. And then if you kept going, you'd see a 10, an 11, and then you'd be back up to the 12 at the top. So again, rotating that way is called clockwise, but we're not using the clock to tell time, so we don't really care about that at this point. What we're going to do is cut up or divide up this clock into a couple key sections. So first, we're going to cut or draw a segment all the way from the left side where the 9 is, through the middle, all the way to the right side where the 3 is, which will basically cut the clock into a top half and a bottom half. Now, we're going to do that just for convenience here. And when we cut it that way, notice then, if you look at the top half of the clock, we have 6 numbers on the top half, of course, 6 numbers on the bottom half, or you could say 6 sections between the numbers if you want to call it that way. And if we cut it that way, let's recognize a couple key places. I'm going to start on the right side of the clock where the 3 is. If we start on the right side where the 3 is, and then noticing that there are 6 sections in the top half of the circle, we could call that starting point 0. If I move up to where the 2 is, the next number in a counterclockwise direction, then that would be what we could say is 1/6, right? It's one of those sections in the top half of the circle between the numbers, so it's 1/6. If I kept moving to where the 1 is, then we could call that maybe 2/6. Which, yes, you could reduce to 1/3. Okay, and if we kept going to the top of the circle where the 12 is and continued to count by sixths, we have 1/6, 2/6, we would have 3/6 at the top. Of course, that reduces to 1/2. And if we keep counting by sixth in this direction, moving on where the 11 is, we would have 4/6, which, yes, could reduce to 2/3. If we kept going around to the 10, we would have 5/6, which can't reduce, so we'll leave it as that. And then all the way down to the left side where the 9 is, we would have 6/6, which, yes, is just 1. So what we're seeing here is a little odd because we don't normally do this with a clock, and that's understood. What we're doing is simply counting by sixths in the top half of the circle, starting from the 3 on the right side as 0, and then counting up by sixths as we move all the way around that top half of the circle. Now, we're going to even continue this by moving to the bottom half, continuing around the left side where we were, where we left off at the 9, okay, which was 6/6 or 1. Next would be, well, 7/6, where the 8 is. If we kept going, again, just counting by 6, we would have 8/6 next, where the 7 is. Of course, that can be reduced to 4/3. Down at the bottom, we would have 9/6, which, yes, could be reduced to 3/2. And then continuing on, yes, even go further, all the way around to where we began, we're going to go with 10/6, where the 5 is, which could be reduced to 5/3. And then there'd be 11/6, which can't be reduced. And then all the way back to where we started, which you could call 12/6, or in other words, 2, if you reduce that. So these fractions are most of our special fractions, not all of them, but I want to note that it's really the reduced versions we'll be using. What I mean by reduced is, we started with 0, and then we went up to 1/6, and then we had 2/6, but we used it as 1/3, we reduced it as 1/3, and we had 3/6, we reduced it as 1/2, 4/6 was really 2/3, 5/6 was reduced already, 6/6, which is really 1. Going around the left side now downward, we have 7/6, which can't be reduced, 8/6 reduced to 4/3, 9/6 reduced to 3/2, 10/6 reduced to 5/3, and 11/6 couldn't be reduced. So highlighting all those reduced ones, and then of course 12/6, which is really 2. Those highlighted reduced versions of all those sixths that we counted all the way around the circle, those are the first set of our special fractions. So if you want to see that again, maybe pause and rewind to make sure that the counting by 1/6 all the way around is clear enough to you, and that's where we're getting all those numbers. They're not just falling out of the sky, they're just counting up by 1/6 and then of course reducing those that can be reduced. Now, unfortunately, these fractions will not cover all the ones that we need, so we're going to have to add a few on here. So again, imagine starting from 0 on the right side where the 3 is, but this time, instead of sixths, we're going to cut it in fourths. That is like the whole circle. So that means we're going to have to put an extra mark somewhere between the 1 and the 2. That would be like 1/4 of the top half of the circle. Of course, the next fourth would show up at the top of the clock where the 12 is. The next fourth would be between the 10 and the 11, and then the next fourth would be where the 9 is at the left side. So we're going to have to add a layer of fourths on this clock, which already had the sixths counted and labeled on it. So let's mark those fourth places on here as well, counting from 0, starting at the right side, where the 3 is. The first fourth would be 1/4. That is the marking between the 1 and the 2. The next fourth at the very top would be 2/4, but 2/4 reduces to 1/2, and hey, we already have that labeled because it was 3/6, which also reduced to 1/2. So we're good there. The next fourth, the place between the 10 and the 11, would be then 3/4. Again, just counting by fourths, and if we can reduce, we will. And then all the way down the left side, where the 9 is, we would have 4/4, which of course is the same thing as 6/6, which is just 1. So these extra fourth fractions or fourth slices are what we have to put in there. Now we're going to continue this pattern going around the bottom of the clock as well. The next place we're going to have to put a fourth would be between the 7 and the 8. So we'll put another mark there. The next fourth would be at the bottom where the 6 is. The next fourth would be between the 5 and the 4. And then the last one would be where we started up at the 3. And so you can see these markings kind of slicing the clock in different ways. So after 4/4 on the very left side where the 9 is, the next fourth marking would be 5/4. That's between the 7 and the 8. The next one at the bottom would be 6/4, which reduces to 2/3, which we already had as the reduction of 9/6, right? Continuing on, we'd have 7/4 at the next fourth place between the 4 and the 5, and then of course 8/4 where we started and where we finish, which is the same thing as 2. So we've already reduced that one as well. So we go back through and highlight these newly added fourth fractions. So with the 1/4, the 2/4, we already had that reduced as 1/2, so we'll leave it as that. 3/4 on the upper left side between the 10 and the 11. 4/4 we already had reduced to 1. 5/4 between the 7 and the 8. 6/4 at the bottom, which we already had reduced to 3/2 above. 7/4 between the 5 and the 4, and then 8/4, which is already reduced to 2. And so if we highlight all of those fractions, those are our special fractions. Now, if you look at the full labeled clock image or circular image with all those special fractions on it, it can look a little cluttered. The key is to remember where those fractions came from. All we're doing is counting. Now, a little oddly, we're starting on the right side of the clock where the 3 is. We're labeling that as 0. But you'll see why eventually we're doing that, okay? All we're doing is counting either by sixths or by fourths all the way around the circle, and then reducing any fractions that can reduce when we get those. That produces the list of what we're going to call our special fractions. The reason that we need these fractions is actually incredibly important, but you'll get to see that eventually. For now, we're just kind of seeing where the fractions come from, and we'll build more into them in the future. All right, our next highlight to consider in this section is what we're going to call, in number 3, coordinate points. Coordinate points of the unit circle. So the word coordinate is not new in math. You've likely seen the coordinate plane, the XY plane, the Cartesian coordinate system. There's a few names for it. And it's typically used for graphing equations and things, or points. Well, we're still going to be using that kind of setup in what we begin to understand for trigonometry. So first of all, let's recall that a circle with radius 1 centered at the origin has the following equation. So you may recall this from algebra class. That basic circle equation is x squared plus y squared equals 1. And of course, there's some algebra behind that we're not going to dig into. The radius is 1. That's why you see the 1 over there. That's always r squared for an equation of a circle. And so if you take a basic image of a circle centered at the origin with radius 1, you'll notice it has a few points that we could plot. So on the right side, it has the point 1, 0. At the top, it has the point 0, 1. Again, using just the x, y setup of the coordinate plane. That's what we're working with here. On the left side, it would have the point -1, 0. And then at the bottom, it would have the point 0, -1. And that's just the basics of a circle with centered at origin and radius 1. Notice that looks amazingly close to our clock. Okay, so that's kind of where we're going with this. But this is now the more algebraic approach or look at such a circle. We're going to be building a lot more in with this kind of algebra and even those kinds of fractions that we saw in the clock. But for now, we're just doing an introductory on it. Now let's do some examples that help us use some of this information. The first one says this: show that the point, and now it's giving us a point in coordinate form x, y, and the point given is -5/13, 12/13, meaning -5/13 is the x coordinate, 12/13 is the y coordinate. And so that point is a point that you could plot with an xy address or coordinate system. Right, we in the circle above plotted just the basic ones that have all the 1s and 0s in them. They're kind of easy because it's easy to mark those on a grid. Taking the point, negative 5/13 and 12/13 for those coordinates would be a little uglier to try to plot by hand, but we could, maybe with the aid of a graphing, electronic graphing calculator or something, plot such a point with some accuracy. Now this question says to show that this point is on the unit circle. Well, this unit circle is what we just looked at above, and we have the equation for it, also recalled, the x squared plus y squared equals 1. So to show that this point is on there, first of all, if it is on the circle, then it must satisfy that circle's equation, which is what we have. So all we need to do is bring back the equation of the unit circle, x squared plus y squared equals 1, and substitute the values given for x and y in this coordinate point in for x and y. So instead of x squared, we're going to put negative 5/13 squared plus, and then instead of y squared, we're going to substitute in for y the y coordinate given of 12/13. And then we're wondering, really we should put a question mark above the equal sign, because we're wondering, does this equal 1? And if it does, then that's proof, or that's how we would show that this point is indeed on the circle. So let's evaluate this. The first fraction is negative 5/13 squared. Now when you have a negative sign in parentheses that you're squaring, that means you're squaring the negative, which would make it positive. That would give us 25 over 169. That is, 5 squared is 25. 13 squared is 169. So that's really what that first fraction is. The second one being 12/13 squared would give us 144, that's 12 squared, over 169, that's 13 squared again. And we're kind of, again, wondering, does that equal 1? Well, let's put these together. To add fractions, you need a common denominator, which we have. They're both 169. And so I just add across the numerators to get the result. Well, 25 plus 144 is 169. So guess what? We end up with 169 over 169, which indeed is 1. So there, we've shown that actually this point is on the unit circle, because when plugged into the equation for the unit circle, it does come out true. Basically 1 equals 1. Our next example is going to be the following. It says the point P on the unit circle, or the point P is on the unit circle. Find this point P in the form of x comma y from the given information. Okay, so again, if we know it's on the unit circle, then everything we just saw above applies. We know its equation, the unit circle, and we know what it looks like. And we know that if we plug in coordinates, we can find, whether they're on the circle or not from that equation. Now, the first one, it's the first piece of information. It says the x coordinate of P is positive, and the y coordinate of P is negative square root of 5 over 5. So if we again bring in the equation for the unit circle, that is x squared plus y squared equals 1. And since this problem gave us the y coordinate, we'll plug that in for, well, the y variable in this equation. So we'll be able to say x squared plus, instead of y squared, I'm going to put in negative square root of 5 over 5. That's the y coordinate they're giving us. And then we know that that squared should equal 1. So we're just substituting the y coordinate given into the y variable of our equation for the unit circle. And of course the goal is to find the x coordinate so that we know the full point, x comma y, right? They already gave us the y, we got to find the x. Well, notice we have x as the only unknown in this equation now, so it's a little bit of algebra. Let's solve for it. If I rewrite this as x squared plus, if I square this coordinate that they gave us for y, okay, so notice it's already negative. If I square it, it's going to be positive. If I square the square root of 5, it's going to be 5. And then if I square the denominator of 5, that's going to be 25. And that equals 1. So far we have x squared plus 5/25 equals 1. Of course, 5/25 could be reduced as well. So we could rewrite this as x squared plus 1/5, that's really 5/25 reduced, equals 1. Okay, if we start over, let me restart with some more space here. If I have then subtracting 1/5 from both sides just to get the x squared alone, then we really end up with those 1/5 canceling on the left side. We have then x squared all by itself equals 1 minus 1/5. Of course, we would need a common denominator to combine those fractions, so we'd have x squared equals 5/5 minus 1/5, which means x squared equals 4/5. And we're getting there. We want to find the value for x, which means we'd want to take the square root of both sides. So we could do that next in this equation. And if I take the square root of the left side, I'll end up with x, because the square and the square root cancel. However, as a result of that, I would have to put a plus or minus on the right side. There's some algebra history behind that issue, but hopefully that sounds familiar. You have to do a plus or minus when taking the square root of both sides of an equation. Of course, then I take the square root of that right side. The square root of 4 is 2, and the square root of 5 we can't reduce. So we'll leave it as plus or minus 2 over the square root of 5. Now, what you will typically see in a problem like this with most trig books is what's called rationalizing. So to rationalize the denominator, we would multiply by the square root of 5 over the square root of 5. This is called to rationalize the denominator, and it's just kind of a standard practice you'll see in most math books, which means this is really plus or minus. We take what we're working with here, plus or minus. On top, if I multiply my answer of 2 over square root of 5 by this root 5 over root 5, on top I'd have 2 root 5, and then on the bottom, root 5 times root 5 is just 5. Now, if we go back to where this problem was, you'll recall they gave us some extra information. They said that the x-coordinate of p is positive. We didn't really do anything with that yet. But this is why that matters. We have two options, but we're only going to use the positive version of it based on that indication they gave us. So what that means is if we put this all back together, then our point P of x comma y is really the point x, but the positive version that we found here, which is 2 root 5 over 5. That's after rationalizing. And then comma y, which they had already given us, so we'll just copy it in. It was negative root 5 over 5. And so this is the final address or form of our coordinate point x comma y for the problem given the information they provided. Now let's try another one of these. Similar kind of problem, right? We're still kind of in the same subheading of this problem where it says the point P is on the unit circle. Find this P of x comma y form from the given information. We just did part A. Part B says the x coordinate of P is, and then they give us negative root 2 over 3, and the P lies below the x-axis. Okay, so like we did in the previous one, if they gave us a coordinate, this time it's the x coordinate, we can still plug it into our equation. So let's bring it back. We have x squared plus y squared equals 1. This is the equation of our unit circle, circle centered at origin with radius 1. And this time they're giving us the x coordinate, so we'll plug that in for x, which means I'm going to write negative root 2 over 3 in parentheses, and I'm going to square it to plug that in for x, and then plus y squared equals 1, and we're trying to find the y value, which means we've got to solve for it, kind of like we solved for x in the previous one. So let's simplify a little bit. If I'm squaring the negative square root of 2 over 3, first of all, squaring a negative will be positive. If I square the square root of 2 on top, I'll get just 2. And then if I square the 3 on the bottom, I'll get 9. And then we'll keep this going with plus y squared equals 1. Again, we're trying to solve for y, so we'll subtract 2 9ths from both sides. Those 2 9ths will cancel on the left side, and this will leave us with a y squared on the left side equals 1 minus 2 9ths. Of course, that's really the same thing as y squared equals 9 9ths minus 2 9ths to get a common denominator, 9 9ths being 1. which means y squared really equals, on top we'll subtract the 9 minus 2 to get 7/9. And then of course we'll take the square root of both sides to get y by itself. Whenever we take the square root of both sides though, we have to use the plus or minus, so we'll remember that as well. And we'll say y equals plus or minus the square root of 7 over, this one reduces. On bottom it's the square root of 9, which is just 3, which means you would not need to rationalize this. Usually they'll only have you rationalizing the denominator. That means you're basically writing it so that it's not a root, as we did in the previous example here. That's a little skill from some algebra here. And now with this y value being plus or minus the square root of 7 over 3, let's also remember that they gave us more information. So if we go back up here to the problem, they said that p lies below the x-axis. What does that mean? Well, below the x-axis, in this region below the x-axis, the y values are always what? They're always negative. So that means we're only going to use the negative version of our answer because of that extra information that they gave us. P is below the x-axis. It's got to be the negative version of it. So with that being said, we can put this all back together. Let's go ahead and write our point in its final form. They had given us the x value, which was the negative square root of 2. Negative square root of 2 over 3. That was the given x value in this problem. We found the y value to be negative square root of 7 over 3. And so that's our final coordinate point that we needed to find. Okay, so with those examples in place, go ahead now and try some of the homework problems. See if you can use these to work your way through it. Of course, with any questions, you'll have to reach out and I can provide some help on those. But these should get you going, hopefully in a good direction. Again, these special fractions that we started with at the beginning, we're going to pick up with those and use them quite a bit. They're going to end up being like the foundation of pretty much everything we do. So this is definitely important. I'd recommend writing it out a few times. Maybe draw your own blank, circle and try to label these places on it. We're going to do that a lot more going forward and use those fractions quite often.